Okay, let's continue to breathe. So, with our breathing, it has different ways of not only just providing us with oxygen and a way for carbon dioxide to escape. You could have situations where you're actually adjusting other things in your body, such as, for example, pH, by adjusting the levels of carbon dioxide. So for one thing, if your body is hyperventilating, so you're breathing very rapidly, you end up pushing out or expelling carbon dioxide from the body faster than it's produced. So you do need to have a certain amount of carbon dioxide in the blood, and that helps with our pH. But if you don't have enough of it, then, here we go, your blood carbon dioxide levels drop. So when we get to that carbonic acid equation, you'll understand this better. So the pH is going to rise, so it's going to become less acidic, and that's going to cause the cerebral arteries to constrict. So they're going to become smaller because the pH is wrong, so protecting the brain. So lack of blood flow to the brain or cerebral perfusion, causing dizziness or fainting because they're not getting what they need. So if you have the person breathe into a paper bag, then they'll rebreathe the expired carbon dioxide, since it's just like a air sac, so they can breathe into it and breathe it back in. That helps to return their levels of carbon dioxide back to a more normal level. So one way that our body is able to even determine our body's pH is using chemoreceptors. So these are receptors that detect chemicals. So we have some that are in the central nervous system, so they're looking at the pH of the cerebral spinal fluid. So these are actually in the brainstem. So that pH is just a reflection of the carbon dioxide levels in the blood, because our cerebral spinal fluid, if you remember from whichever chapter that was at the end of AP1, the cerebral spinal fluid is filtered out from the blood plasma. So that's how it should be a good close enough approximation. So that's where that's going to, that's just one way of measuring that. So with these central chemoreceptors, they help with communication to the respiratory centers in the brainstem, like I kind of glanced over earlier. So to adjust our respiration level, so our breaths, essentially breaths per minute, or breathing rate, so that you can maintain a certain level of carbon dioxide in the blood, so your pH is correct. Outside of our brain, we have what's called the peripheral chemoreceptors. So again, they're still receptors. They still detect chemicals, except for they're on the outside, if you will. And these, instead of just your carbon dioxide level, like your central ones, your peripheral ones will detect both oxygen and carbon dioxide in your blood. So these peripheral chemoreceptors are located in the carotid and aortic arteries, so these big chunky ones on top of your heart. So good indicator of what's still there, how much oxygen you have, especially as in these are the big ones that are going to your body. So aorta, the rest of the body, carotid going toward your brain. Another receptor that can be stimulated is the stretch receptors. So as you breathe in, these receptors are determining how much stretch has happened in your lungs. So this is a reflex that will control how much air can come into the lungs. So basically, so you don't like blow up your lungs because you keep breathing in. It's like, okay, there's a stopping point. Stop. Another reflex is the irritant receptor. So this is any kind of junk that's in the air. For example, like smoke, dust, pollen, fumes, stuff like that. Cold air, too much mucus. So they're going to trigger a protective reflex, as in this is the stuff that we don't want to get down into the actual lungs, possibly getting into the bloodstream. So reflexes, we have bronchoconstriction, so taking our airway passages and making them smaller. Shallower breathing, so not getting as deep a breath, so you're just kind of barely having a exchange of gas in the lungs. Holding your breath, especially if it's something that has a strong negative like stench to them. So that's also called apnea. So if you ever heard of someone who has sleep apnea, it's because they're not breathing when they're at sleep. So, okay, so holding your breath or coughing to get rid of the crap out of your lungs. So we can control at least our breathing rate, and that is from our motor cortex, and that helps to go to our skeletal muscle that helps with our breathing. So able to have control over our ability to when we do breathe in and out. So there are some limits. So for example, if you hold your breath, eventually your carbon dioxide levels are going to increase because they're not being expelled out. There is a autonomic control that's going to override that and force you to breathe. So no matter how much your little kid decides, I'm going to hold my breath until I get my way. Doesn't matter. Your body's going to force them to breathe. You'll be fine. Okay, let's finally get into the actual process of breathing and how we actually move air in and out. So using our pressure gradient. So I'm just going to kind of go over this so you can understand this concept. So our airflow is depending on our pressure gradients and how much resistance. So if there's a bigger difference in pressure gradient, so for example, a quiet breath versus a big inhalation, you have a bigger pressure difference in that big inhalation because you've expanded your thoracic cage or your chest region more larger than just a normal breath, and so you're going to bring in way more airflow. So there's going to be a bigger difference in pressure, so a bigger flow of air into the lungs when you're making that nice big breath. Another one is resistance. So with our airway flow, so our bronchioles, those can change in their diameter. So if they have reduced in size, such as bronchoconstriction, that's going to make it harder to breathe. So for example, like those irritant receptors, one thing that they can do is make stuff smaller, therefore harder to breathe in. That's why, your kids who get asthma, they get all huffing and puffing, that wheezing situation, because they're trying to force air flow through smaller airways that have constricted because something that they breathe in has gotten to those irritant receptors. So one thing that helps with our breathing is we have to adjust the pressure in our lungs based on the atmospheric pressure. So this is the pressure of the air. So all that tall column of air above us, how much pressure that is. So if you are at sea level, that measurement is 1 atmospheric or 760 millimeters of mercury. So that's the pressure amount. So there's a higher pressure difference, so it makes it easier to breathe. So you have higher pressure outside the lungs, so you don't have to drop your internal lung pressure that much. So it's easy to breathe there. Opposite situation. So you are in Denver, Colorado, so up high in the mountains. The atmospheric pressure there is 633 millimeters of mercury or 0.83 atmospheres. So it is a lower air pressure, and so you have to drop your air pressure in your lungs even further in order to breathe air. So it just makes it harder to do so. So I'm going to go over this. You don't have to know like what Boyle's law is, and then the next one I'm going to get on the other page. Another slide. Bad. So this is just looking at how pressures play a role. So for Boyle's law, it has to deal with the volume of air that you're dealing with. So you will still have the same amount of air particles. So whether it's carbon dioxide, whether it's oxygen, whatever those air particles are. So if you take the same the same quantity of gas and you change the volume, it's going to change the pressure. So even though it's the same amount of air, if you increase the volume, you're increasing the space in between those little air molecules. So it's just empty space. So because there's less of those air molecules banging up against each other, so they kind of can just free flow around and not hitting each other, and so therefore not bouncing also into the contents, the outer walls of whatever container they're in. But opposite situation, if you decrease that volume of air, that's going to increase the pressure, because now there's less space in between those air particles, and so they're going to be bumping around against each other as well as the walls of whatever container that they're in. So here's a simplified version. So some of y'all got kids. If you don't have kids, at least you grew up as a kid. So depending on the space that you have is going to determine your level of pressure. So lungs not breathing. So if you have like a regular play area, so that's the house and your driveway. So moderate amount of space, moderate amount of pressure. So this is kind of like your house rules. Okay, you have certain things. Don't do this, mom's cool. Let's say I increase the volume or the space. So let's say you live in a cul-de-sac and all the families in that cul-de-sac, they're okay with the kids running around in their driveways, using their lawns, whatever. So you have more space. You have less pressure, so less rules. Do what you want. However, let's say it's raining outside and you're stuck completely in the house. So you don't even have this extra driveway space and yard to play around. So in this case, you'd have stricter house rules. So you'd have more pressure. There's less space to move around. You can't throw around a ball. You can't get on your bicycle. So that would be a more pressurized situation. So let's look at breathing. So at rest, no oxygen exchange because there's no difference between the air on the outside and inside of your lungs. However, inspiration, we increase the volume. So more space. That decreases the pressure inside the lungs. So when it drops below your atmospheric pressure, air is going to move from a higher atmospheric pressure down the pressure gradient and into the lungs. For expiration, so we're breathing out, we have compressed our thoracic cavity, so our chest area, so we have decreased lung volume. So we have less space to be in. That causes an increase in lung pressure. So if we increase lung pressure larger than the atmospheric pressure, then air is going to move down its pressure gradient from higher area in the lungs and out towards your atmosphere, so your regular air outside your body. So here's just another slide that describes the changes in volume and pressure and where airflow is going, as well as sometimes what actually helps with your ribs. They also move out the way. That's going to also increase volume, which decreases pressure and allow air to come in, versus opposite situation where the ribs are going to fall back down, decreasing your chest volume or thoracic cavity volume, which increases the pressure, and so air is going to move out, and then you start out this process all over again. So that's just another visualization of that. So let's focus on inspiration for right now. So with our inspiration, so normally at rest, we have a intrapleural pressure that helps to keep our lungs open. So if you ever get stabbed in the lungs, especially if you're breaking this pleural cavity, that's going to cause this negative 5 centimeters of water. So that's just the pressure measurement that they use, since air doesn't have much push, so it can't really push around mercury. So you get stabbed, you don't have this pressure, this negative pressure that helps to keep the air open, so that's how your lung ends up collapsing. So that regular intrapleural pressure, that just allows for your lungs to stay open, so it makes it easier to actually change your respiratory volumes and therefore change your airflow in and out. Okay, so these next few, they just talk about your anatomy of what pulls on what. I'm more interested in understanding the changes in volume and how they affect pressure. It's just here you're talking about the specific anatomical parts. So for example, remembering we talked about the pleura of your lungs and how one layer, your visceral one, sticks to the lungs, the other one sticks to your ribs and chest region. So when the muscles move those bones of your ribs, that parietal pleura is stuck to them, and so they're going to move, and it's going to pull on the visceral one and causes changes to the volume of your lung. So that's what that is going into. Another thing with inspiration, this is a bunch of physics stuff that big whoop. Okay, so there's another physics law that plays a role and has to deal with temperature. So when you inhale air, your body's going to warm it up because your body's just warmer, typically warmer than where you are, unless you are middle of summer in Arkansas and it's super hot. Okay. So that warm air is going to increase in volume because the molecules are moving more. So it's also going to take your normal, regular tidal volume. So you're in and out, kind of like, tide, like on a beach with waves. So that regular 500 milliliters of air will expand to 536. And it helps with inflating lungs. So helping with that, increasing the volume of your chest area, and therefore helping to bring air in as well. So, in quiet, regular breathing, you're not running, you're just chilling out. You don't really need too much oxygen because you're not making a bunch of ATP to feed your muscles. So, that regular volume is called tidal volume, and that is 500 milliliters of air. So, that's 500 milliliters that gets into the entire respiratory tract. So, that doesn't mean that all of that 500 milliliters actually get into your alveoli. But we'll talk about that in a second. Okay, well, maybe not in this video. Expiration, so breathing out. So relaxed breathing, very passive. Remembering your lungs are elastic, so they pop back, and that recoil helps to compress the lungs, so decreasing the volume. When your volume decreases, your pressure increases, and it's just enough so that air can float down its pressure gradient and out of the lungs. You can force air out, so using those chest and abdominal muscles to push and greatly press on the lungs. That's going to decrease the volume, increasing the pressure, and therefore air moves out, which is at a lot faster rate because you have a greater pressure gradient. Last thing for this video is looking at resistance to airflow. So we've changed our volumes. We can change where air goes. However, the other thing that can affect it is resistance. So, depending on the size of our bronchioles can determine whether air can actually move, because that's how it gets to the lungs. So, one thing is bronchial diameter, and the other one is pulmonary compliance, so how stretchy our lungs are. So, our bronchioles can be changed with their diameter using bronchodilation, so dilating, making something bigger. So the way this is done is using epinephrine. So your sympathetic nervous system, getting you ready for fight or flight, can actually stimulate this to cause your bronchioles to dilate, come larger, and so therefore allowing for more airflow, getting the oxygen to your oxygen to your muscles so you can run away. This is also what's inside those EpiPens. So those kids or adults too, who have allergic reactions and can have extreme bronchoconstriction because they have, down here, either anaphylactic shock or asthma. That's the EpiPen that it's going to do is going to cause that bronchodilation. So open up those airways so they can actually freaking breathe. Okay, opposite situation. Instead of bronchodilation, we have bronchoconstriction. So constrict, like a boa constrictor, the snake squeezes on those bronchioles, so we have less airflow able to go through. So decreased airflow. So areas where this is, we have histamine. So part of that is allergies, and then also released from blood vessels as well. Parasympathetic nervous system, so calming the body down. You don't need all that oxygen. Cold air, just because that is a irritant, and so that's going to cause your bronchioles to dilate. Chemical irritant, so again, your irritant receptor, same thing, cause bronchoconstriction, decreases airflow. An extreme version of this, which could possibly lead to suffocation. Therefore, if you do need an EpiPen, keep it with you, please. Thank you very much. So this is anaphylactic shock. So people who, for example, are allergic to peanuts or bees can actually have that fast of a reaction. So you shoot them with that EpiPen, they have bronchodilation. Unfortunately, that only works for about 30 minutes. So basically, just enough time to hopefully get them to the hospital. So if you're out hiking and it's going to take you a while to get from wherever in, boondocks you are, you might want to bring at least an extra one just in case. Okay, then same thing with asthma. It's an allergy situation. Next thing dealing with our airway resistance is pulmonary compliance. So how stretchy are our lungs? So a nice healthy lung is nice and stretchy. A diseased lung isn't so much. So generated lung disease or scar tissue, so you have damage to your lungs aren't as stretchy, they're not able to change their volumes as much, so it causes the inability to breathe, but it decreases your ability to breathe. Another thing with our compliance or our stretchiness is the inside of the air sacs, the alveoli, there is a layer of water on there. So for example, I might as well say it here. That's down there. It causes surfactant. So it reduces your tension in that air sac, so it allows for that stretchiness. So instead of them, instead of the water layer, because that helps with our gas exchange, we'll talk about that later. Instead of that water layer, that surfactant on the inside of your lungs help to break up those hydrogen bonds, so keep them from holding hands, because if not, they would keep things nice and tight. So that surfactant helps to break that apart. We need the water molecules, however, we don't need them holding hands the whole freaking time. So break that apart, allowing for your alveoli, so those little air sacs, to expand or compress when necessary. Some preemie babies, so my respiratory therapy people, sometimes you have to give artificial surfactant to a preemie because they haven't made that surfactant yet, remembering that your lungs are the last thing that develops in a preemie baby, and so there's some stuff that they're just not able to do yet. So you have to give that to them so that it helps them with their breathing. Okay, and we're going to start with alveolar ventilation on the next video.